All right, I got 3 kids, ages 20, 18, and almost 12. Back in the early O's, I used to stroll my little kids around. My older kids, I stroll them a lot along the river all the time. And so here I am strolling my kids. That's Henry right there, my 20-year-old, back 18 years ago, 19 years ago, whatever. And you can't see me. I'm not going to try to draw me. But you draw this pink thing here is the force I'm applying to the stroller as we walk by the river near the library on a beautiful fall morning. Okay? And so some things are happening here. We got my force down an angle of 32 degrees. Okay? Pushing down like this. 44 Newton force, which is not that much, maybe about a 8 to 10 pound force, something like that. We're moving forward. Initial speed is 1.37 meters per second. Also not too remarkable. And I'm going to push Henry a grand total distance of 1.13 meters. Also not too impressive. All right? And the question is, which forces are acting here? I mean, obviously my force is acting, but what others? And can we find the total net work done? Finally, we're going to find my final speed after I travel through a distance of 1.13 meters. Okay, that's the deal. What are the forces acting? Well, there's the pink force F that I've already drawn. I'm going to draw some more pink forces. There's going to be a normal force up on wheel 1, right? Contact force with the ground. Actually, there's 2 wheels there. Let's just stick with the drawing here. Maybe I'm pushing them on a 2-wheeler. Who knows? And there's another force pushing up on this wheel, normal 2. We don't know the values of those. Oh, we also, there's something that I left out, which is that the mass of the whole kit and caboodle here, Henry plus stroller, the whole mass is going to be equal to 22.7 kilograms, which is also just about right. Okay. It's actually like 50 pounds, so maybe Henry's gotten big. You know, maybe this is 2002 or 3. Whatever. Doesn't matter. Okay. So we want to know what the forces are. So we got these 2 normal forces up, right? Keeping the cart going, I mean from falling through the concrete. We also have mg down. So we got 4 forces acting here. We've listed them. I'm not going to list them, but I've drawn them. There they are. My force down and to the right, an angle of 32 degrees down, 44 newtons. 2 normal forces pushing up, 1 weight of gravity down, and we're assuming no friction here. So we're all good. Okay, that's it for the forces. Okay. 4 forces acting. Now, of these 4 forces, normal 1, normal 2, weight, and my push force, F, which one of these forces does work? Which ones of these forces do work? Well, looky here. Here's the displacement vector. Notice that 3 of these forces, N1, actually I think I want to use the yellow marker here, N1, oops, N1, N2, and Mg are all perpendicular to the displacement vector. Right? Displacement vector is in the positive x direction. N1 and N2 are in the positive y direction, the perpendicular. Mg is in the negative y direction, also perpendicular to D. So the work done by these forces, right, work is Fd cosine of theta. In all 3 of these cases, the angle between the force, okay, which is N1, N2, or Mg, and cosine, and the displacement is 90. Right? Now, don't be confused here. This F here is not that F there. This is just a generic definition of the work. Okay? Generic definition of work. And so this is whatever force is doing the work in question. So if we were calculating the work done by the first normal force, this would be N1. Actually, let me draw it that way. I think I'm doing okay on time. So the work done by the normal force 1 is the normal force 1 times d times cosine theta. See if I can fit this in down here. Work done by normal force 2 is normal force 2 times d times cosine of theta. The work done by gravity is mg d cosine theta. That fit? Yes. So these three forces are all perpendicular to the displacement. Normal force number 1, normal force number 2, and the weight. Normal 1, normal 2 are up, weight is down. So in all three cases, this angle, theta, turns out to be 90. So that's 0, that's 0, and that's 0. So none of these three forces do any work. The only force that does work is my force, because all the others are perpendicular to the displacement. Okay? Whenever they're perpendicular to the displacement, always, forces perpendicular to the displacement never do work. Never. Okay? So the only force that does work is my force. So if that's the only force that does work, then the net force the net work, rather, is my work. Because all the other ones contribute nothing to the total work. So the net work is going to be F d cosine theta. And now this F and that F are the same. My force has a magnitude. These are magnitudes, remember. It's 44.0 newtons. Displacement is 1.13 meters. Cosine of what? What's the angle for this force? For this work? It's 32, right? Because displacement is to the right, and my force is down, right? Displacement, remember we can move vectors around. So if you want to, you can move the displacement vector up here. Tail to tail. With the force vector, that angle is 32. So cosine 32 degrees. When you do that, you get 42.2. You get 42.165 joules, which we will call 42.2 joules. So my work is the net work. And the net work done on the stroller by my force and by all forces, 42.2 joules. That's the net work. That's it. Okay? So that's the answer to part A. W net, 42.2 joules. So second part, we want to find V sub f, the final speed. We know the initial speed is 1.37. We want to know the final speed. Well, we're going to use the work energy theorem to do this. And remember, the work energy theorem is work net equals delta K. Well, look here, we've already got the left-hand side of the work energy theorem finished. We're actually going to use the 42.165 and then round at the end. But we got the left-hand side of the work energy theorem completed. So this side is done. Now we need to find delta K. Delta K is always final minus initial, which is always 1/2 mvf squared minus 1/2 mvi squared. Okay. And that is going to equal 42.165 joules. Okay. So let's apply. So let's use the work energy theorem here. We have work net here, 42.165. So I'm going to rewrite the work energy theorem here. Work net delta K. That's our principal. That's our starting point. So we have 42.165 joules equals delta K. Let's go ahead and put some numbers in here. We're not going to do the algebra. We're not going to do symbols to the end. We're going to put some numbers in. So 1/2 mvf squared, 1/2 mass is what? 22.7 kilograms times vf squared, which is the thing we want, minus 1/2 mass we know. Pardon. Mass we know, 22.7 kilograms. VI we know, VI is 1.37. And look, everything's numbers except for the thing we're looking for. Okay. So let's see what we got here. Do I have, no, I didn't break it down any further. Okay, so you can multiply your 1/2 by your 22.7 here, and you can multiply those numbers out. You can get numbers, and what you're going to end up with when you solve this for V sub f is the square root of 5.592 meters squared per second squared. And then when you take that square root, you're going to get V sub f is 2.36 meters per second. That's my final speed right there. Okay, so we found our left-hand side here. Right. We have our right-hand side here. So we got both those checked off. Okay, and all we had to do was to set these two equal, because that's what the work energy theorem tells us to do right there. And then turn the crank, solve for what we need, which is V sub f. Again, you find the net work, put it on a shelf, 42.2 joules, or 42.165 joules. You take the right-hand side, you find delta K. You set them equal. Do the algebra. So I'll leave you with this one last thought here, which is rather important. Delta K is always going to be equal to this. Work net is always the more difficult side of the work energy theorem. Work net is always the more difficult one. There's more steps to it, requires more thought. Delta K is always, always, always that. Right here in the double box, or double oblong shape, whatever you call that shape. Okay, that is always going to be delta K. Left-hand side, work net, requires a little more cogitation. So that's it. All right, another example. We'll have plenty more of these coming, I assure you. All right, this is how you start to solve problems using energy. We used very few forces. Once we got our free body diagram here, we didn't have to worry much about forces. Okay, solving with energy sometimes, in many ways, is a simpler thing because energy is a scalar, not a vector. All right.